Okay, so today we're diving into something pretty fascinating, typological grammar. And for those listening in, especially if you're coming from a philosophical background and you're always drawn to those deeper structures, the underlying framework of things, think of typological grammar as a way to really break down how we figure out if a sentence is grammatically correct. Not just in some, abstract logical sense, but in the way we all actually use language every day. We're going to explore those core ideas, see how they've been expanded, and really try to wrap our heads around how this connects logic and language at a very, very deep level.
Absolutely. For those of you who really love to get to the bottom of things, the foundations of understanding this deep dive is going to be right up your alley. Typological grammar isn't about rote memorization of rules. It's about the search for those underlying logical frameworks that might actually give rise to those rules. In a sense, we're trying to understand the essence of why some sentences make sense and others just don't.
So where are we headed on this journey? Well, we'll start with Lambeck's work, his early systems for grammar. From there, we'll move on to some of the ways typological grammar has been extended to tackle some of the more complex parts of language, like word order and meaning. And then we'll touch on the logical tools that are used to analyze these systems. So let's start at the very beginning.
Right back to the late 50s, early 60s with the work of Jim Lambeck. What's particularly interesting is his initial goal, which was to create what he called an effective rule, basically a logical test to separate the sentences that are grammatically sound from those that aren't. And this wasn't just about formal logic. It was aimed at the messy complexities of natural language.
So he wanted a way to look at any sentence and be able to say, yes, this is grammatically correct, or no, this doesn't work. And he wanted that decision to be based on logic.
Exactly. And his big insight was to treat the parts of speech, like nouns and verbs, those building blocks of language, as formulas within a logical system. So now the question of whether a bunch of words together make a grammatically correct sentence becomes a question of logic. Can we derive that sentence type from the types assigned to the individual words?
So it becomes a deduction. Like if these are the types of the words, then this must be the type of whole sentence.
Precisely. To do this, Lambeck came up with these fundamental operations for building types. You have the product operation, usually shown with the symbol ear. You can think of that as the ordered combination of linguistic expressions. And then you've got division, left division, and right division. These kind of represent what's needed linguistically. So for instance, you might have a verb phrase that needs a noun phrase to its left to become a sentence right. So that might look like NPS. It needs a noun phrase to its left. And when you actually combine that verb phrase with a noun phrase, well, the division operation makes it happen, and you end up with a complete sentence.
Right. It's like a slot that needs to be filled. You have a verb phrase that's incomplete, and then the noun phrase comes in and fills that slot, and voila, you've got a sentence.
Exactly. It's like a system of needs and fulfillments built right into the logic.
And to give this all a bit more precision, Lambeck actually drew on ideas from modal logic. He imagined a model where linguistic expressions are treated as resources. And there's this special relationship, a ternary relation called R, that represents how things get combined grammatically. It's like that merge operation you hear about in linguistics.
Right. So if you have RXIZ, that means that expression X was made by combining expressions Y and Z in that specific order. And now the truth of statements about these complex types depends on that ternary relation. For example, an expression, let's call it X, is of the product type AB only if it's formed by combining some Y of type A and Z of type B using that special R relation. So you're really getting down to the structure of how these expressions are built.
That makes sense. You're not just saying these things exist together. You're saying this was built from these other things in this particular way.
Right.
Okay, so we've got the types, we've got these operations, and this view of grammar in terms of how things combine. And Lambeck created a minimal logical system around all this. It's called NL, which stands for the non-associative Lambeck calculus. But one of the really interesting things from a philosophical point of view is what NL deliberately leaves out. Things like contraction, weakening, exchange, and associativity. So no duplicating words, no ignoring words, no swapping them around without consequence, and no regrouping things freely. Why is this absence so important?
Well, that's where we get to this idea of NL being resource sensitive. And that's really significant because it means every single element in a derivation has to be used. And it can only be used once. You can't just duplicate words or throw them away or move them around without potentially messing up the grammaticality of the sentence. Each word really matters. It plays a specific and unique role. And that's a bit different from more traditional logical systems where these structural rules are kind of taken for granted.
It mirrors that sense we have about language, that every word contributes something distinct. And it reminds me of Occam's razor a bit, in the sense that it's avoiding unnecessary complexity and redundancy in the system.
Absolutely. And then there's also these residuation laws, which are really fundamental to the whole thing.
Right, you mentioned those earlier.
Right.
What do they tell us about the system?
Well, the residuation laws define how the product and division operations all relate to one another. They kind of formalize the idea that these operations are deeply connected, like inverses of each other. For example, the idea that A can derive C given B is logically the same as saying A combined with B can derive C, and also that B can derive A under C. These laws are what allow us to really work with these linguistic types and make logical deductions about them.
It's all very tightly connected. It sounds like this isn't just some loose set of ideas. It's a very rigorously structured logical system.
Right. And what's really cool is there's actually a soundness and completeness result for NL. This means the rules of the system perfectly match the intended interpretation of how things are combined grammatically. So what you can prove as a well-formed sentence using the logic is exactly what holds true in all the models of grammatical combination we've talked about.
Wow, so it all really hangs together beautifully. The system itself, the interpretation, and what it can actually prove all align perfectly.
Yes. And from these very basic principles, NL can then give rise to other universally valid principles of type combination. These are like fundamental logical properties that are true no matter what specific language you're looking at, like the principle of application, which is how a function combines with its argument, and lifting, which is like treating an argument as a function over a function that needs it.
Okay, so we've got these general logical principles that hold across languages, and then you mentioned this idea of radical lexicalism, right? It's the idea that the grammar of a language isn't mainly a set of overarching rules, but rather it resides in the lexicon. It's the types assigned to individual words that really drive the system. So whether a sentence is grammatically correct comes down to whether you can logically deduce a sentence type from the types of the words in it.
Exactly. A lot of the burden of grammatical description is shifted to the lexicon. And what's really interesting is that you could potentially even learn the lexicon automatically. You could use these type equations to figure out what types should be assigned to words based on how they actually combine in real sentences.
That's pretty mind-blowing. You could throw a bunch of sentences at the system, and it could figure out what the logical types of the words need to be to make those sentences work. It would be learning grammar through logic. And you said that basic grammatical concepts just kind of emerge naturally from this type structure. Can you give some examples of that? I think our listeners who are into philosophy would really appreciate that.
Absolutely. Let's take the concept of valency, for example. That's how many arguments a verb needs, like whether it needs a subject, a direct object, and so on. In NL, an intransitive verb like sleeps might have the type NPS. That means it needs one noun phrase on the left to form a sentence. And a transitive verb like sees could have the type NTS, NP, so it needs a noun phrase to the left and a noun phrase to the right. The requirements are baked right into the types themselves. You don't need a separate rule that says this kind of verb needs these things.
It's like the logic itself knows how many arguments the verb should take.
And you can also look at the difference between complements, which are essential parts of a phrase, and modifiers, which are optional. Complements help satisfy the valency needs of a head word. So if a verb needs a direct object, the complement is that direct object. But modifiers, on the other hand, often have types like AA or A. That means they combine with something of type A and they give you back something else of type A.
It's like adding a little extra information without fundamentally changing what the thing is.
Right.
Okay, that's pretty neat how those basic grammatical concepts just fall out of the system. What about those more complex things like filler gap dependencies? Those are things like relative clauses, like the book that I read where there's a missing piece, or what, like questions like who did you see?
You can handle those with types that involve these nested implications. It's like they're signaling that something has been extracted from a certain position. For example, the relative pronoun that might have a type that indicates it combines with a sentence that's missing a noun phrase in the direct object position. And by combining with it, it creates a noun modifier.
So the type itself is keeping track of where that missing piece should be.
Okay, so we have this logical system, NL, and we understand how it handles basic grammatical structures. But how do we actually determine if a sentence with its assigned logical types is truly grammatically correct according to NL? I mean, is there some kind of proof procedure?
Yes. Lambeck actually reformulated his system into something called a sequent calculus. A sequent is a statement that looks like this. XA, X represents the sequence of types representing the words in the sentence, and A is the type we're trying to derive. Usually that's going to be the sentence type S.
So it's like asking, can we get to S from X?
Right. And the cool thing about the sequent calculus is that you can get rid of certain steps in a proof without changing the outcome. That's called cut elimination. And what that means is that any valid derivation can be transformed into a proof that only uses the subformulas of the original statement. So you get a very clear, direct proof. So no roundabout ways of getting there. It's the most direct route from the types of the words to the sentence type. And that gives us a way to actually decide if a sentence is grammatically valid according to this system.
Exactly. It's a decision procedure.
And you mentioned earlier that there's actually a whole hierarchy of different Lambeck calculi. What are the key differences between them?
So you start with NL, which has no associativity and no commutativity. But then you can start adding those properties back in. If you add associativity but not commutativity, you get L. If you add commutativity but not associativity, you get NLP. And if you add both, you get LP.
Oh, hold on, just to make sure I'm following. Associativity is about how you group things, right? Like in math, it doesn't matter if you add 2 plus 3 first or 3 plus 4 first, as long as they're all being added together. But commutativity is about the order, right? Like 2 plus 3 is the same as 3 plus 2.
Exactly. And in these calculi, they represent different theoretical views on how grammatical composition actually works. So L, for instance, treats concatenation as associative but not commutative. LP, on the other hand, treats order as irrelevant grammatically, though it can still be relevant for meaning.
Right. The order of words in a sentence usually matters a lot. Which brings us to a pretty big question. How do these logical derivations actually connect to the meaning of the sentences they generate?
That connection is where the Curry-Howard correspondence comes in. It's often summarized as formulas as types, proofs as programs. It shows that there's this deep link between derivations in these categorical grammars and the lambda calculus. And what that means is that the logical steps you go through to combine words into a sentence have a direct equivalent in how their meanings are combined. The structure of the proof itself shows you how to build the meaning of the sentence.
So the syntactic derivation isn't just about showing that a sentence is well formed. It's also like a blueprint for how to understand the meaning of that sentence.
Exactly. There's a systematic mapping between the syntactic types and derivations and the semantic types and lambda terms. For example, a noun phrase NP might map to a semantic type that represents entities, and the sentence type S might map to the semantic type for truth values.
Okay, so the syntactic types are guiding us towards the semantic types.
And the directional slashes in the syntax guide us towards functions in the semantics.
I see. It's like the slashes are telling us how to put the meanings together. Now, you mentioned before that there are some limitations to this derivational semantics because of the resource sensitivity of these logics.
Right, because every element has to be used exactly once. Sometimes it's hard to explain semantic things that seem to involve reusing information or maybe even getting rid of some information. Think of quantifiers like every or some or certain kinds of adverbs.
So if you've got a word like himself that seems to refer back to something already mentioned, the logic might have trouble with that because it wants to use each word only once.
Exactly. That's where lexical semantics comes in. Instead of just relying on the meaning you get directly from the syntactic proof, you can assign more complex lambda terms to specific words in the lexicon. This lets us handle words whose meanings are a bit more intricate, like reflexive pronouns, quantifiers, and relative pronouns.
It's like giving those words special instructions for how they contribute to the meaning. Okay, so we have the basic Lambeck systems, and we see how they connect to meaning. But now let's move beyond the basics and look at how typological grammar has been extended to deal with some of the more difficult and philosophically interesting aspects of natural language.
This is where things get really exciting. While the basic Lambeck systems are powerful, they run into some trouble when it comes to things like discontinuous dependencies. These are cases where words or phrases that are related to each other aren't right next to each other in the sentence. Like in questions where you extracted a phrase like, who did you see? Where who is the extracted phrase. Or situations where you have infixation, like in some languages where a word gets inserted into the middle of another word.
So you have these non-local relationships that are important for the grammar and meaning, but they're not right there next to each other. That's a real challenge.
Exactly. And it raises all sorts of questions about how linguistic meaning is structured and encoded. So how have typological grammarians tried to solve this?
That's what I'm dying to know.
Well, one approach is multimodal systems. Instead of having one set of operations for building types like product and division, you have multiple families of these operations, and each one might be governed by different structural rules.
So it's like having different modes of combining things.
Right. Each mode would have its own version of product and the slashes, and they would interact through these well-defined postulates that let you combine them.
So it's a way to have more fine-grained control over how things combine.
Exactly. Like, to handle extraction that's not at the edge of a sentence, you might use a discontinuous mode of composition. This mode would allow the extracted element to be linked to that gap in the sentence, even though they're not right next to each other.
So the logic is basically saying, okay, in this particular mode, you can jump over some things.
Right. And then you have another strategy that involves control operators. These are kind of inspired by modal logic. They're like unary operators, for example, oo and and they can change the types assigned to linguistic expressions.
Like adding a little flag to a type to say, hey, this one behaves a bit differently.
Exactly. Their meaning often involves an accessibility relation, which is similar to how modalities work in modal logic. And you can use them to either allow or block specific structural operations. Like, oo might say, okay, this constituent can be extracted, while oo might define an island where you can't move things out of it.
So instead of having completely separate modes of composition, you have these operators that control how the normal composition rules work.
Right. It's a bit more modular.
And it's all still within this rigorous logical framework. Okay, that's multimodality and control operators. What about that logic of discontinuity itself? How does that deal with these split linguistic structures?
That brings us to the discontinuous Lambek calculus, or DL. It was pioneered by Morrell and others, and it's a direct extension of the associative Lambek calculus L. The goal of DL is to handle those split strings formally. These are expressions where parts aren't next to each other, but they still form a single grammatical unit, like that idiom, take to task, where you've got the verb take, and then later on the prepositional phrase, to task.
Right, and those two pieces really belong together even though they're not right next to each other.
Exactly. And to model this DL has these new type-forming operations like Ryu, which is a wrapping product. It lets one constituent wrap around another. And then it's got U, which is for infixation, and U, which is for extraction. And these are specifically designed to deal with these cases where things aren't contiguous. And a really key innovation in DL is how it uses these multi-sorted algebras that have a special separator symbol. So the sort of an expression tells you how many of these separators it has, and that represents the points of discontinuity.
So a normal sentence with no discontinuity would have a sort of 0. But to task would have sort of 1 because it's got that one spot where something can be inserted.
Right, and the meaning of the types is defined in terms of these sorted domains. And DL has been really good at analyzing lots of discontinuous phenomena like particle shift, where you can say, call Mary up or call up Mary, and the different ways that quantifiers can scope over parts of a sentence.
It sounds like a powerful way to analyze these non-local relationships. And then there's this symmetric categorical grammar. What's the main idea there?
Well, symmetric categorical grammar, and in particular the Lambek-Grisham calculus, or LG, offers a really different perspective. It challenges that traditional idea in logic that an inference leads to just one conclusion. In LG, you can have multiple formulas on the right-hand side of the inference, and these are combined using a multiplicative disjunction, which is represented by Ilhera.
So instead of one output, you can have multiple potential outcomes.
Exactly. It's a big shift. And LG also doubles the type-forming operations. So you've got the familiar product and divisions, but then you also have a second family of operations that are related to the first set through a kind of symmetry where you reverse the arrows. And there are special interaction principles that show how these two families work together.
Okay, so it's like you've got two sets of operations that mirror each other, and they interact in very specific ways. But how does this help us understand language?
Well, these interaction principles are really good at explaining things like infixation and certain kinds of scope ambiguity. They allow for really interesting interactions where one element can reach into or combine with another element in ways that go beyond just simple concatenation. And this is different from the continuation-based approaches we'll talk about later.
So LG is giving us a new way to think about how these elements interact. Now, you mentioned flexible interpretation and continuation semantics. What are those about?
Those address those situations where You can't really map syntax directly to semantics. You need a bit more flexibility. So flexible interpretation says that one syntactic type can actually have multiple semantic types that it maps to, and these types can shift depending on the context.
It's like the syntactic type is just a starting point, and then the meaning can adjust based on what's going on in the rest of the sentence.
Right. There are these type shifting principles like argument lowering, value raising, and argument raising that let these expressions adapt their semantic roles. So you can treat things more uniformly even though they might seem different on the surface.
So a noun phrase might always have the same syntactic type, but its underlying semantic type can change depending on the situation.
Exactly. And then continuation semantics gives us a really powerful way to understand this kind of flexibility. The idea is that the meaning of an expression doesn't just depend on that expression itself. It also depends on what comes after it in the sentence. It's like what happens next in the interpretation process. And this approach is great for things like scope ambiguity, where different ways of evaluating those continuations can lead to different readings of the same sentence.
So the meaning isn't just contained in the individual words, it's also determined by how those words are put together and what follows them.
Exactly. It's all about the context. And in this framework, all types are basically given an extra continuation argument. And this makes it really flexible. It lets you handle all sorts of ambiguities and phenomena where the order of evaluation really matters. And interestingly, even LG, which seems pretty different, has a natural interpretation within this continuation passing style.
Wow, this is a real deep dive into logic and language.
Yeah.
We've gone from these foundational systems to all these extensions that try to deal with some of the most complex and subtle aspects of language.
And we've seen how closely related these things are.
Absolutely. Now, I'm really curious about how all this abstract stuff relates to how we actually process language in our minds. You mentioned proof nets earlier.
Right. Proof nets are a way of visually representing logical derivations, and they avoid some of the problems you get with the standard sequent calculus where you can have multiple different ways to derive the same thing. They were originally developed for linear logic, and they really capture the core logical structure in a clear and intuitive way. And what's fascinating is that how we build these proof nets as we process a sentence step by step might actually reflect something about how our brains are working. The complexity of the proof net might even correspond to how difficult it is to process that part of the sentence.
So those garden path sentences where we think we're going one way and then we have to backtrack might be reflected in the way these proof nets are being built up.
Exactly. And for the more complex, calculi, the rules for checking if a proof net is correct, get more complicated.
I can imagine. Okay, so we've talked about the expressive power of these systems and how they might connect to language processing. What about the computational side of things? Can we actually use these frameworks to analyze language with computers?
That's a really important question. The original system, NL, is actually computationally very efficient. It's equivalent to context-free grammars and has a polynomial time recognition problem. But when you add associativity, like in LGL, it becomes NP-complete. That means it can get much harder to compute as the sentences get longer. And for the multimodal and symmetric systems, it gets even more complex. It really depends on the specific constraints you put on the system. Some versions are mildly context-sensitive, which means they're still reasonably efficient. But others can be as powerful as context-sensitive grammars or even Turing-complete, which means they can compute anything that's computable.
So there's this constant balancing act between wanting to capture the complexity of language and meeting the system to be tractable enough that we can actually use it. It's a fascinating challenge. Yeah. Now, finally, you mentioned some other frameworks that are related to typological grammar.
Yes. There's combinatory categorical grammar, or CCG, which is also based on categories and rules for combining them. It's been traditionally more rule-based than the purely logical approach of typological grammar, but they're actually becoming more similar now with the use of multimodal control in CCG. And then you have pre-group grammars, which are a simplified version of the associative Lambic calculus L. They're very efficient for parsing because they relate to context-free grammars and push-down automata. And finally, there's abstract categorical grammar, or ACG, which is a really high-level abstract framework for defining grammatical systems. ACG separates the abstract types and operations from the concrete words and phrases, and it uses mappings to connect them. So it's got this idea of compositional interpretation, like typological grammar, but it's more flexible in how it derives the surface forms from the abstract meaning.
So there's a whole family of these formal systems all trying to capture the essence of how language works. This has been a really incredible journey into the world of typological grammar. We've covered the basics all the way to some incredibly complex extensions, and we've seen how it relates to meaning processing and computation.
And I think what's most remarkable is how it shows this deep connection between logic and language. It's really an attempt to understand the logical foundations of how we communicate and how we think.
Absolutely. And for our listeners who are interested in philosophy, I think this is a really rich area to explore. It raises all sorts of questions about the nature of thought, the structure of language, and the relationship between them. And it makes you wonder, are there truly universal principles of grammar that underlie all human languages? Can we capture those principles in these logical frameworks? These are big questions that are still being actively researched. So if you're fascinated by this, I encourage you to read more about it.
And keep those philosophical questions coming. This field is all about asking those deep questions and trying to find rigorous and insightful answers.
Thanks for joining us on this deep dive. Until next time, keep exploring and keep thinking deeply.